Okay. Okay. Thank you for the people that are joining already. So I'll just wait for more people to join in. I'll wait for more people to join in. Okay, thank you, those people that are joining in. Thank you. I'll just wait for some more people to join in. Why? Okay. So thank you for all those people that are joining in. So let me share my screen. All right, so this was where we stopped in the last class. So using the forward rectangular rule, for the forward rectangular rule, instead of this integration here, you are replacing it with the area under the curve, but it's just at the time when the integral starts, just at minus k minus 1t, and instead of this t, it's k minus 1t multiplied by t, because you are considering the area. That's for the forward rectangular rule. So that was where we stopped in the last class. So we stopped here that y, this particular y of kt minus this is equal to this. That's using the forward rectangular rule. So if you look at this particular equation here, a multiplication by z raised to power minus 1, it represents a delay of t seconds. So basically what we are saying is that the z transform of y of kt is y of z. The z transform of this. So because you have a delay of minus 1, the z transform is z minus 1 y of z. So the z transform of this is y of z, but you have a delay of minus 1. So this is where the minus z comes from. Then this is where the z minus 1 comes from. Then the minus a comes down. Then this t comes down. So the z transform of this, of u of k, the z transform of u of kt is u of z, but you have a delay of minus 1. So that's z minus 1. If to say it was, you want to find the z transform of k minus 1, 2. So the z transform of this is going to be equal to, z minus z raised to the power of minus 2, then y of z. So that's how we do the z transform. If you want to do the z transform of z minus, instead of 2, you have 3. Then the z transform is given by z raised to the power minus 3 y of z. Then the z transform of, so there's the z transform of y of kt is equal to y of z. So I hope you just understand, because here is also the same thing as, so instead of k, so this is the same thing as y k minus 0, then multiplied by t. So what you have here, so since you don't have any delay, in this, so the z transform of this is just y of z. Then if you have a delay, is given by z. Yeah, we have a delay of 2. So the z transform is this. So if it was a delay of 1, so if it was k minus 1, so the z transform is going to be this. So I hope you all understand what I said. So given the explanation I made, the z transform of this highlighted, the z transform of this highlighted function, so the function I highlighted, is given by this. So just look at the explanation I've made and you will confirm that you are correct. Then from here, if you make y of z, if you collect like terms, you make, because y of z is common, then if you collect u of z, because we want to get the transfer function, you have this. Then when you do some manipulations, you will get this. Then if you multiply both sides of this highlighted equation by z minus 1, you get this. Then if you divide both sides by t, you get this. Then finally, the transfer function we got is this. Then if you'd observe, this was where we started from. This was the transfer function we started from. And in the z domain, this was where we ended up with. You can see that you have a here, you have a here, then you have s. So in order to convert from the s domain to the z domain, you can just say that let s be equal to z minus 1 divided by t. So for the forward rectangular rule, you are going to equate s. Instead of s, you're going to replace it with z minus 1 divided by t. So somebody will ask that, like the other time, if you are to memorize the proving, the most important thing is you understand it. Because for the forward rectangular rule, you replace s with z minus 1 divided by t. For the exact approximation, you replace s with this. So, and I said that using this is quite complicated. So we had to use some approximate methods. So for the forward rectangular rule, you're going to replace s with z minus 1 divided by t to get your z transfer function from the s transfer function. So for the backward rectangular rule, in the backward rectangular rule, you are going to use the right side of the time, of what you have on the time axis. So for the forward rectangular rule, we use k minus 1 t. But for the backward rectangular rule, we are going to, in place of this t, we are going to replace it with kt, and we are going to replace it with kt, where kt is the time at the end of the integral. So the difference between the forward rectangular rule and the backward rectangular rule. Somebody asked me, does s vary in the forward rectangular rule? Yeah, s is the same thing. It doesn't change. To answer your question, s doesn't change in the forward rectangular rule and also in the backward rectangular rule. S is the same thing. So for the backward rectangular rule, instead of t, you are replacing it with kt. You're replacing it with kt. Then you have to multiply by t, because you are replacing this integration with this particular function. And like we did the other time, so yeah, I'm just repeating what I wrote here. Then yeah, I made you do the inverse, the z transform of this. So it's similar to what we said in the last one. So the z transform of this is y of z. The z transform of this is this. The z transform of this is this. While the z transform of this is this. So it's similar to what we did. Then you collect like terms, separating the y of z from the u of z. Then you put it in the form of the transfer function. So if you put it in the form of the transfer function, you are going to get this. Then if you divide both sides by t, you get this. Then if you multiply out just this portion, if you multiply this portion by, you multiply both numerator and denominator by z, you will get this. So for the backward rectangular rule, the transfer function is given by this, and this was the transfer function we started with. So if you compare both of them together, you have a here, you have a here, which is the same thing. You have a here, and you have a here, which is the same thing. So S, it means that S is equal to this particular one. So for the for this rule, for the backward rectangular rule, you replace S with Z minus one divided by TZ. That's for the backward rectangular rule. So we'll be doing an example so that you understand better. Then for the trapezium rule, for the trapezium rule, you replace the integral. You say that the integral is divided by this. So you consider, let me go back to the figure. So you consider the time stamp at the start of the integration, and you consider it at the end of the integration. For this forward rectangular rule, we are only considering it at the beginning of the integration. For the backward, we are only considering the time at the end of the integration. But for the trapezium rule, we are considering both time at the start and at the end. So let's go back to the derivation. So since you are considering the time at the start and at the end, then you divide by 2, because to get the area is for a triangle is t divided by 2. So instead of multiplied by t, is t divided by 2. So that's the logic we are going to go through. So y of t, please ma, can this card be posted for download? Yes, it's going to be posted. After I finish, I'm going to send you the video file for it. So so we are replacing this integration with this. So you consider t at the start, that's k minus 1t, and you consider t at the end, which is kt. You consider this one at the, start, k minus 1t, and you consider it at the end, k of t. Then you divide all of them by, you divide it by t, you multiply it by t divided by 2. Then, so this equation is just the same thing with what you have here. Then the z transform of this is given by this. So I will not go over it again. Please explain that last part again, okay? So for this, we are using the trapezium rule. And for the trapezium rule, we want to do this integration. So to do this integration, we are just going to evaluate this function at both the start of the integration and at the end. So this minus ay of t, it becomes this, because you are evaluating it at the start of the integration, which is k minus 1t, and at the end, which is k of t. Then this also is replaced with this. So you are evaluating it at the start and also at the end. Then you have to multiply everything by t/2 because you are considering the area under the curve. So that's how I got this. Then, so this is what we got. Then you find the z transform of this. So I've explained it previously. Like the z transform of this, the z transform of this is given by this. So since we are dividing both everything by t/2, so we just put the t/2 here. So I've already explained how to get from the time domain to the z domain. So let me just explain it again. So if we have u minus k minus 1, so the inverse z transform is this u. So if it was k minus 2, so the z transform is going to be z minus 2. So using this approach, the one I just typed, you can see how you move from here, which is in the discrete time domain, to here, which is in the z domain. So you can just follow in the class. You can just, after the class, you can just try to follow along how we did that. Then you collect like terms. You collect the y of z terms and the u of z terms together. Then you get the transfer function as this. Then when you divide both sides by this, you're going to get this equation. Then after that, this particular side of the equation, if you multiply it, if you rearrange it, you're going to get this. Then so the transfer function is given by this equation 9. So we started with this equation. So this equation is in the continuous time domain, is in the Laplace domain, while this is in the z domain. So if you compare these two equations, just like we did, we would observe that S is equal to this, is equal to what you have here. So in the Trapezium Rule, you convert from the Laplace domain or the S domain by saying that S is equal to this. So we've gotten the tree method now. And of all the three numerical methods, the forward, the backward, and the bilinear transformation, the best approximation is the Trapezium Rule or the bilinear transformation. And the reason why it's the best is because it doesn't overestimate or underestimate. When we started, I said that this one underestimates because the area where my cursor is pointing is not covered. So it underestimates. This one overestimates because this part of where my cursor is not part of the area under the curve. So it's overestimating. But this is the Trapezium Rule. So it's better, it's the best approximation compared with the forward and the backward. So we said that the trapezium approximation is the best approximation. So it's actually the best approximation of the tree method. So I've been proving for a long time. So let's do an example so in this example, which is example 2, you are giving this transfer function, and this transfer function is in the S domain, is in the Laplace domain. And you are asked to use the 3 different numerical methods to find the discrete approximation for the poles of the system. So remember, the poles of the system is the denominator. It has to do with the denominator. Then the B part says that you should find the exact transformation for the discrete poles. So now we are asked to do this using the 3 methods. which are the forward rectangular rule, the backward rectangular rule, and the bilinear transformation. So that's what we are asked to do. So somebody said, aside needing the proof to understand the methods, are we going to prove any of the methods in the test exam? That's a good question. So the answer to your question is you need to first of all understand it, because when you understand it, then if you are asked to prove it in the test or exam, if you are asked to prove it in the test or exam, then it will be easy for you to prove. So, and another, the answer to your question is that you have to know this. You have to know the 3 solutions. So instead of memorizing it, so you have to know this. This is for the backward rectangular rule. Then this is for the forward rectangular rule. Then this is for the exact transform, exact Z transform. So you need to know it. So the answer to your question is, instead of trying to memorize it, you can also learn how to prove it so that you don't have to memorize it. So this is the solution to the trapezium rule. So you have to know it. And if in knowing it, you decide to learn how to prove it, then that's also okay. Okay, so this is the second example, and we're asked to transform it to the Z domain, just the poles only. Then if you factorize the question, this is the denominator. Then if you factorize it out, you are going to get this. So if you multiply this and this together, you're going to get the original question. You get the original question. Then from your 412, I want to get the frequency. That's the natural frequency. So if you compare this with this, and you will see that the natural frequency is given by 0.282 radians. The reason why I'm trying to do this is because I want to get the frequency. I want to get the frequency. And since we've gotten the natural frequency as this, the frequency F, you can just simply get it by this. So the frequency is 0.1138. And you know that the reason, okay, let me tell you the reason why we are doing this. The reason why we are doing this is to get the sampling time T. Because, you know, I'm sure you might have done this. You need to sample. So let me just write. So the sampling time should be greater or equal to, so if f of s is your sampling time, and this is the highest frequency, the sampling frequency f of s should be greater or equal to 2 times the highest frequency of the signal. So our frequency is given by, because in the question you are not giving the sampling time to use. So in a way, we have to work out the sampling time. So if you are not giving the sampling time, which is the case in this question, you have to work out the sampling time. So we've worked out the frequency as 0.131. Then in order to choose the sampling frequency from the Nyquist criterion, so you guys, you've done digital signal processing, the sampling frequency should be greater or equal to 2 times the highest frequency. So since this is the frequency, our sampling frequency should be greater than 2 times of this. And for this question, we just we choose a sampling frequency of we choose a sampling frequency of 1/8 because obviously 1 is greater than 2 multiplied by this. So to be on the safe side, we just choose this particular sampling frequency. Then if this is the sampling frequency, to get the sampling time is just 1 divided by 1, which is 1. So a sampling time of 1 should be adequate. And the reason why we need to get the sampling time is because we need T, we need the sampling time. T is the sampling time for the forward, backward, and the Trapezium Rule. How did we get these parameters? Okay, from your 412, you know, when we started this course, I said that this course is just a continuation of what you did in 412. That's 412 was in continuous time. Then this course is in discrete time. So I got this equation from control system. So that's why I just rushed over it. You would have been familiar with this if you go back to your notes. Your control systems in 412, you'll be familiar with this. So that is how I got these parameters. Okay, so we already concluded that we can use a sampling time of 1 because 1 is definitely greater than the frequency we arrived at, which is greater than 2 times this. Then we need the sampling frequency. For the forward rectangular rule, we need T. For the backward, we need T. And even for the trapezium rule, we also need T. So that's why we needed to find T first. So if T wasn't given in the question, you have to choose a reasonable value of T. Like in this case, T was not given in the question. So we chose our T as this. Then S is the poles of the system in the S domain. So the poles of the system are this. So you get the poles by just equating this, what you have here, by 0. So the system in continuous time has 2 poles. Then using the forward rectangular rule, you have this. You know, you want to convert it in the Z. So if you make Z the subject of formula here, you get your Z to be equal to this. Then when you just put in the formulas, if you track through the algebra, you will see that your Z is equal to this. So for the backward rectangular rule, S is equal to this. Then if you cross multiply and make Z the subject of formula, you get this. Then when you do the mathematics, I will not explain it because it's just after the class, you can just go over it. You get Z to be this. Then if you use the trapezium rule, for trapezium rule, S is equal to this. Then you make Z the subject of formula. So when you make Z the subject of formula, you get this. Then you put in the values. I will not explain it. It's just maths. You're going to get this. So when the class is over, you can just go over the mathematics. So for the trapezium rule, you get this. Then you know you have to get the exact approximation. So for the exact approximation, you simply use this. Then, like we did, you plug in the value of S. You know, S is equal to minus 0.2 plus or minus J 0.8. Then our T is 1. So you can track through the mathematics, you get this. So in summary, using the 3 different numerical methods, for the forward rule, we got our Z to be this. For the backward rule, we got our Z, the poles of the system to be this. Then for the trapezium rule is also called the Thomson's rule. So for the trapezium rule, we got this. And the exact approximation, which is the most correct approximation, we got this. Then this class is on the Z transfer function. Like we'll have another class, 2 more classes. After that, we do stability. I will not go into stability, but actually this in the S domain, in the S domain, we got our pose to be this, and this is stable because in the S domain, the real part of the pose should be negative for stability. So you should have done that in 412. So since this is negative, we know that the system is stable. For the Z domain, is a different ball game altogether. So we do that. We have two more topics. After that, we do stability. I will not be explaining that, but this particular one is stable. This one is stable. This one is stable. But this particular one is unstable. So I will just leave it at that. We'll do stability proper next. Two more lectures away. So you can see that the three methods, they gave different approximations, and they're giving different approximations. Then we are going to find out why they are giving different approximations. We're going to find out that later. So that's not the subject of this class, but the subject of this class is just to know how to convert from this S domain into the Z domain. Then another method you can use, when we started discrete approximations, I said that you can use numerical integration, which is this, and you can use the pole zero mapping. So the pole zero mapping is very easy. So Zoom is telling me I have 8 minutes. So I'll just rush through it. For the pole zero mapping, these are the steps you follow. So you map the poles using the exact transformation. You map the zeros also using the exact transformation. Then you map all zeros at S is equal to infinity to Z is equal to -1. Then you get the gains. So I'm rushing. So I will just, because I just want to complete this class. I don't want a third part. So let's do a question for the pole mapping. So now we're using the pole mapping. So we are in the S domain, the Laplace domain. So we want to get the Z transfer function. But in this question, we are giving the sampling time. But in that former question, we're not giving the sampling time. So if we're not giving the sampling time, you have to get it on your own. But if you are giving, then you use the sampling time given to you. Then the first step is to map the poles using the exact transformation. In the exact transformation, Z is equal to, so in the exact transformation, Z is equal to minus ST. So our S here is -5 and -10. So you simply replace S with -5 and -10. So when you do the algebra, you get this. Then for the pole zero mapping, if you have two poles, then definitely you have 2 zeros. In the question, you have 2 poles. So definitely you have two zeros, because the number of poles is mapped with the number of, should be equal to the number of zeros. So that's why you also have, you have 2 zeros, and you always map the zeros to Z is equal to -1. So that's why you have this. Then there's a K you need to determine, which is the gain. So in order to determine the gain, this is the S transfer function in the Laplace domain, and this is the Z in the Z domain. So for this part, you will evaluate as S is equal to 0, and here you will evaluate as Z is equal to 1. So when you do the arithmetic, so which I didn't do, you will get your K, your gain, to be equal to this. So using the pole zero mapping, yes, somebody asked that, will this lecture be available? Yes, it's going to be available. So with this pole zero mapping, you got your K to your transfer function to be equal to this. You know, for our first method, what we did was that we put this into partial fractions when we started. So this is using the first original method we did. So this is the question. We put it into partial fractions. So we got this. Then you convert this into time domain. You inverse Laplace transform this, you get this. Then when you convert from the time domain into the Z domain, so you use your tables, you're going to get this. Then when you do the mathematics, this is the Z transform you would arrive at. So as you can see, when you use different methods, you actually get different answers. But the method you use is going to be given. So in the question, if you are to use the post zero method, the forward rule, the backward rule, or the trapezium rule. So somebody asks, why are we doing this? S is equal to 0 and Z is equal to 1. So the reason why we are doing this is because I skipped through the rules. So the rule says that in order to get the gain, you should evaluate G of S at S is equal to 0, and you should evaluate G of Z as Z is equal to 1. So that's why we are doing this, and we are doing it to get the gain. So I have less than 3 more minutes. So if there are questions in the chat, I'll look at the chat now, and if there are any questions, I would answer them. I will answer it. So while I wait for questions, after the class, I'm going to be giving you the link in order to view the lecture, so that you can refresh your memory. Then for this class, I skipped a lot of there were quite a number of things I skipped, like tracking through the mathematics. Like when you have this, how you got Z, I skipped the mathematics. So when you are learning it on your own, you would try to prove that from this, you can actually get this. Then you also track through the mathematics I did to be very sure that the answer is correct. Because when you are having a test or exam, then this is obviously the steps you are going to follow. Let me check the chat. So, no questions so far. So I'll be ending, if there are no questions, I'll be ending the meeting now. Then I'm going to post the video link to you shortly after this meeting, so that you can view it on your own. So thank you all for the cooperation. And I'm also going to be giving out a quiz. So be on the lookout on Moodle, a quiz and an assignment based on what we've done so far. So thank you all. We'll see you later.